A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude.
Hello, everybody. Welcome to SINFO 27. We hope this is the greatest edition yet. Enjoy it.
Ladies and gentlemen, welcome on stage, Patrika Voiku.
Hello, thank you all for coming here. So my name is Petrica Voicu, I'm from PayPal. I will talk at the beginning a bit of background about my company, about my work. Then I will talk about the challenges that we have and our solution and our approaches. And at the end, I will talk about our latest version of a product we built to solve some of our problems, our scaling problems. A bit about me, I work at PayPal. I am working on a service, database proxy. Pretty much our PayPal services took the databases, most of the databases via this service. In the past, I done various work in other backend services. One of them I would mention is database-backed publish subscribe messages system, no message loss, heavily used at PayPal. I also worked on our POS solution, PayPal Here. I'm a Golang contributor. Prior to PayPal, I worked on various areas, distributed systems, embedded systems, desktop apps. I'm born, raised, and educated in Europe, in Romania. I worked in Romania prior to going to the States. So yeah, if you have questions afterwards about how do I see working in Silicon Valley, coming from Europe, feel free to come and ask after the talk. So a bit of intro about PayPal. We are a global leader in payments in over 200 markets. We are working with over 100 currencies. We have 300 plus customers. We have huge payment volume. Last year was like over 700 billions. We are growing every year. Last year, 25% year over year, and similar growth we had past years. Our site is made of over 2,700 microservices. Over 4,500 engineers are working. A lot of releases last year. A bit about our online databases. So we have thousands of database instances, thousands of nodes, lots of storage, lots of services, billions of calls we are handling every day. Over 300 database schemas. Just key takeaways, I would say it's a massive, massive scale. Also, complexity, dealing with over 200 markets in financial systems. There are a lot of compliance, a lot of regulations, a lot of rules that we have to follow. And we are growing every year. As I mentioned, like 25% typically every year on payment volume. Our user base grows about, I think last year was like 14% user growth. And this is actually impressive given the size. So we have 300 million users over. So at the beginnings, we started like most of other websites. We started small. We had the monolithic architecture where typically users would access our website through desktop, and we had one database. Today, and this is very simplified diagram, we have mobile and access for mobile on desktop, and we have internally we have thousands and thousands of microservices and thousands of databases. I mentioned like 100 database schemas, and so how do we get there? And some of the what challenges do we have? So before that, I would say what do we mean by scalability? Scalability is the capacity of a system to handle increased workload by adding more resources. Ideally, this is how a graph would look like. So the more resources you add, linearly you increase the growth. Like for example, the throughput. You double the resources you may handle. You double twice for example, the throughput. In reality, it's not quite like that. And this is actually a graph how it would look like. When you add more resources, there is some overhead, mainly because of the coordination between those systems, because they are not necessarily independent. And I would make an analogy here. Imagine you have a highway, one-lane highway, and if you add another lane, you don't double the throughput because there is some overhead, people switching lanes, people going on and off ramp. So there is a little overhead, and it's similar here. Of course, if those lanes would be completely independent, every lane would have their own ramp, there will be separators between them, you would scale linearly. But in real life, it's not the case. So I'll talk in detail why scalability is difficult, and I will focus on this talk, of course, on the database scalability. There are many aspects of when we talk about scalability. This is an example of a typical microservice, one of those thousands that we have at PayPal, how they access database. And they typically, there's a client making a request. A microservice will get a database connection, will execute some requests. In this case, example like I have 3 requests, and then it will free up the connection when it's done. Now, if we look at a timing, if we do this way, you can see that the connect takes 100 milliseconds. It takes, sometimes it might take more, while the request can take one order of milliseconds. So we can see that connect is takes quite some time, and it's unfortunate because the actual work is small. So typically, solution in this case, it's you pre-allocate those connections. You have a pool of them. You allocate them at the beginning. And every time microservice gets the request, it will lease one connection. It will use it and will release it. And like in this example, request takes now 3 milliseconds. And not only latency is improved, so request takes 3 milliseconds. This also saves a lot of database load. When you connect to a database, that about 100 milliseconds is because database is doing a lot of work internally. Like for example, for Oracle, they create a process, they pre-allocate a lot of memories, they may do even some queries internally to cache some of the results. And of course, this way you also save that work and you get more performance from your database. And now I want to talk a bit one particular aspect of pool sizes. So this is common practice, and there are for Java, is one example. There are a few common connection pools, third-party availables. You can use them in your application. I mentioned, like you see here, CTP0, Apache, DBCP, or Oracle. They have a lot of knobs you can configure for various use cases. I want to mention there is an anti-pattern, which means a mistake that people makes over and over. And with this, they specify minimum and a maximum number of connections. The idea is that because the traffic is not even always, when your traffic is low, you are using fewer connections. When it's high, then you start acquiring more connections and grow. And sounds good. In reality, it's a bad idea because when traffic spikes, just allocating a lot of connections at one time, it will cause an increased load on the database, and the database performance will degrade. And also another mistake people make, sometimes by mistake, they oversubscribe, which means they configure max too much, and overall, it will actually exceed the number of connections on the database side, and sometimes it's a disaster. And I mean, we have, so at PayPal we have a fixed size, no min and max. And for further explanation and videos and research done, you can take a look at the work the Oracle real world performance group and their further explanations and measurements. Now, let's see how we can improve further. So as I said, you have a microservice at the beginning. You have low load. You configure how many connections you have to the database, and then we scale, and then we add more services, and even more services, and eventually you hit a connection limit because all of the databases they have a limit on the number of connections. Oracle have I believe 15,000. MySQL has they have 10,000. Even some databases, even some of them they don't have specified. You should always have a limit, and after a certain load, actually performance degrades. So in this case, we have to look for solutions. And sometimes, we found that, hey, we can lower connection. Sometimes we allocate maybe too much for each service. So we lower the connection pool size, the number of connections for each microservice. And sometimes we improve the code. So we make better use of resources. Other times we buy better hardware. So the SQL requests are faster, so you can service higher load. This is called vertical scaling. but we found that also we can improve even further. So and this fundamentally is because of the design. The database connection, the connection pool is partitioned. So basically, you pre-allocate to each microservice a fixed size. Now, in reality, sometimes you get imbalance. Sometimes one service may need more resources, more database connections than other. Like in this example, the one at the bottom, maybe all the connections are taken or busy, and there are a lot of few maybe more requests, and it doesn't have connections, and those requests will either fail or have some increased latency. And this is unfortunate because the database connections, the database has capacity. There are connections, but they are actually used by, they are allocated to a different microservice, and they are not used. So we realized, hey, we can have a shared pool. And idea here, we have a service which has all of the connections to the database, and now every microservice, when they need, they will get a connection from this shared pool. And and this helps us a lot. Now we can see that we can also improve even further. If we look at a typical example of a microservice talking to a database, we can see that database connections is idle in between those requests, or either because the service may do some work, or it's the network latency. And it would be nice if we can, when the database connection is idle, we can service other requests. And the solution for this is it's multiplexing. So the idea here is that all these microservices, although they think they have a connection to the database, when they connect to this shared pool, they actually only have it when they actually try to use it. And this is when we allocate the connection to from the database to the client. And in this case, like this connection is used by either microservice whenever it is needed. And this is similar. Imagine a phone switch in an office building where you may have thousands of phones internally, but outgoing to the phone company, there may be only maybe hundreds of lines. And because most of the time the phones are idle, you don't need 1,000 to pay 1,000 lines to outgoing. So whenever somebody picks up the phone switch will connect your phone to the outgoing line. When it's done, it will disconnect. So we've done this at PayPal, and it helped us quite a lot for some use cases. And we wrote this microservice called Hira, which is basically a shared connection pool and multiplexer. We open sourced this last year on GitHub. We want to contribute to the community. So we developed this service a while back at PayPal. This is the last version that we open sourced. Over the years, we had some principles that guide us, some constraints. And the main one is it has to be always correct. It has to be 100% correct. Of course, the other ones are important: resiliency, scalability, availability, performance. It's also important to have a minimal configuration. Although we deploy this in hundreds of databases, so I believe over 300 databases, and they are different, and they have different configurations slightly. But because there are so many, we want to help deployment and have a minimal configuration and default most of it. We also from architecture side, our clients are thin, not a lot of logic there. For one reason is that we have multiple stacks, and I will talk a bit later. We have multiple languages at PayPal, so we don't duplicate the code. And also over the year, we didn't change our protocol between the clients and server. This was quite old protocol, but we noticed that it's quite efficient, small, low overhead. Although we could do better, but it's just the return on investment wouldn't worth it. And so I'll talk also other features. We talked about how we scale databases at PayPal. We talked about the global connection pool. We talked about multiplexing. There are other ways other features we did to help scale. And I'll talk in detail a bit. Read-write split. So this is some of our big databases. We use Oracle RAG clusters, and we noticed after a certain high load, because those nodes needs to communicate, the performance would degrade. So what we do, we send the SQLs or the queries that are writing to one of the nodes in this example, and this is configurable, and the writes to the other three. And this actually helped the database perform better to handle increased load. Another way we do this, imagine some of the microservices are doing only reads, like the one at the bottom in this example. They can read from a replica database, which is read-only, and in this case, we synchronize like every few seconds. So basically, in this case, actually, you double the I would say the workload having two databases. But keep in mind, this is possible when you have microservices that only do reads, like in the bottom one. Next, I want to talk about sharding, and this is one of the features actually the last feature that we wrote. So if we look again, this is how a typical microservice talking to a database looks like. You have multiple microservices talking via this proxy that we wrote to the database. Now, we've done all these improvements to scale. As I mentioned earlier, global connection pool, we did multiplexing, read-write, replicas, and eventually, because we have such a high volume, we cannot scale any further. And the last option we did is sharding. And the idea here is basically you split the database into multiple pieces, and that way you can if you have two pieces, you scale, you can do twice more work, right? In theory. So and the sharding can be done in a client, and it would look like this. So every microservice would decide for every query, will decide to which database it goes, and it will choose the appropriate Hera proxy to use. Or it could be done in the server. In this case, the microservice, they don't know if the database is sharded or not. They just think that, hey, I have a database connection. I just talk to it, and our proxy takes care of the routing to the appropriate shard. And we choose the last option, right? The second option to implement it in the server. And one reason is we have multiple tech stacks at PayPal. We have C++ services. We have Java, Golang, Python, Node.js, and all of them use a thin client, and which, of course, that code is duplicated, but it's very small. It's about, most of the cases, it's about 1,000 lines of code, which is quite minimal. And all the logic we put in the in the server. A bit about details about how we did the sharding, what our implementation. So every request, every SQL must have a shard key, which we use to route. And for this shard key, we apply some math calculations. We apply a hash function to IDI to evenly distribute over maybe 1,024 values. And then we have also another layer of mapping. So for this shard key, when you do the calculation, it will result in a bucket. And then there's another mapping where we map multiple of these buckets to a database shard. And there's another mapping that can be done at the physical layer, depending on what database you have. So why we did this? Why took us so long to do the sharding? What's so difficult? Well, first of all, you have this constraint that all of the requests must have a shard key, and sometimes the business applications, the business logic is complicated, and they may not have, or it's difficult to always use a shard key. Also, it's also difficult to handle requests that span multiple databases, and you have two cases. One case number one is when you do writes, when you have so if you want to do a write on multiple databases, and at PayPal we use database transactions, which is basically you have multiple operations and you do all of them at once or not, because the problem is so complex that we have to deal with. So if you have to do all or nothing into multiple databases, then this not only is difficult, it's difficult to handle the errors, the unhappy case. If you can have a network error or you can have a database condition, but it also doesn't scale well because you have to block a certain connection, a certain database for the entire period. And our solution actually on this one, we don't allow this. We don't, which is of course it puts more pressure on the application side, but we are not doing distributed transactions because they don't scale mainly. As for reading, databases are efficient and for doing reads. They have some internal structures called indexes, right? And they are very efficient for lookups. Now, imagine now you have indexes in different places, and also if you have joins, then that's difficult because I mean it's slow at least because there is so much communication between those nodes. Again, right now we are not handling this. This is done by the applications, but we actually plan in the future to handle a subset of reads. And also another challenge for sharding is that there are multiple points of failure. Any one of those databases can fail. Not only, so you have increased chance of availability loss. Plus, it's also increased complexity for managing those databases from the operational side. So, this is a lot to talk about, but I try to talk about the essentials here. So, sharding, key takeaway, I'll say this is sharding allow you unlimited scalability. You can scale it forever, but it's quite complex. So this finishes the scalability discussion. Resiliency. This means dealing with exceptional cases when you have a sudden burst in load or some SQLs may take longer, or some database or database may have some issues, hardware or sometimes bugs. And what we want in this case, we want to limit the impact, or ideally you want to avoid, but at least to limit. And you don't want a complete meltdown of your system. And of course, when the condition disappears, you want to restore the way it was before, to self-heal. And we have quite a few features here, which I'll talk in a bit of detail. So first one we call bouncer. Idea here that if you have a burst in load and you don't have database connections available, you accept the connection and disconnect it immediately. So basically failing fast. And this is better than not failing fast. At least the existing requests are handling well. Also, clients, they will back off and they will retry later on. After the burst is over. Also, we use a search queue. Sometimes, again, if all of the database connections are taken and you don't have capacity, we put them in a small queue, and if a connection gets become available, we allocate to this incoming request. And if not, we will time out. Typically, if there I think we have a timeout of 1 second, but it's configurable. And if they time out, they will give an error, and the service will retry. But at least the existing requests are handling well. Another features we have, again in this case, when database is overloaded, we realize that if there are certain queries that take a lot of time, this is not ideal, but it's better if we kill that particular query which is doing, is too slow. And instead of that one which may take 1 second, we can handle 1,000 small queries. And this again sounds strange, but it actually helps a lot because you have no other alternative. And this is an example of something that we had in production when it happened a few years back. Of course, there was a small glitch, but it was almost unnoticed versus a complete meltdown where you would have a few maybe queries that will take all the database connections and will keep them forever. Also, we have certain applications that are quite critical, and in that case, you want to have a backup database in case one of them fails. So this service would always work. And so in this example, this application they use two databases. All the logic is in the client, and if database number one would fail, it would use the number one, and eventually we actually moved this feature into Hera to be not only to be used by other languages. This was done in Java first, but also we improved upon it. In this case, if database number one again is fail, all the requests go to number two. It is transparent to the clients. Clients don't know what's happening, or if there's an error or not. And it also self-heals. So when the database, when the first one becomes available or works well, it will be used again. Some other things we've done. So most of the features I talked so far was coming from the client's requirements, either for scale or for resiliency to protect the database. We also done some work to help with our operations engineers. First idea here is that we want to do maintenance without without having a customer impact, without a downtime. We actually recommend our clients which talk to the proxy. We actually recommend them to recycle often, which may sound counterintuitive. We recommend to, I mean, they configure how they want, but it's 1 minute. And it's a bit of overhead, but it's worth it because it is much easier to manage. If you want to do, for example, an upgrade on node number 3, we mark it in the load balancer that node number 3 is going to go away. So all the new connections will be sent to, in this example, to node 1 and 2. 1 minute later, node number 3 doesn't have any connections. And now it can be, for example, upgraded or, and then when it's available, it will again you mark in the load balancer that machine number 3 is going back up, or node number 3 is going back up, and the new connections will be spread even to all of the nodes. And 1 minute later, we have a perfectly balanced environment. Another feature we put there to help our database administrators to do maintenance without downtime. And for example, if they want to do a maintenance, maybe an upgrade or a patch to node 3, they mark into there's a special table that we use, and they mark it there that a certain node will go away at some time and for a certain period. The proxy will disconnect from that node and will actually reconnect to the remaining 3. So all the requests are routed to the available 3 nodes in this case. Clients are not impacted at all. When, of course, when the maintenance is done, Hera will automatically reconnect to this node. So next I want to talk a bit how we wrote the last version of proxy, and when we wrote it in Go language. So we had previous version written in C++, and it was written. The code was asynchronous, and I will talk briefly a bit what this means. And this is scalable. It works at PayPal scale and is efficient, but it's quite complex. And the more we added features over the years, it got more complex. So what do I mean by synchronous versus asynchronous programming? In synchronous programming, you have in this architecture, you have a server listening to a port, and when a new request comes in, when a new client comes in, it will spawn a new process, and it will handle that one process will handle one connection for the duration of the client, pretty much. And an example is this an old inetd, which is with a telnet in or SSH daemon. Also, the earlier architecture of Apache web server would work the same way. This is simple and easy, and but not scalable. And it's easy. In the right side, I have an example typically how the code look like, and it's a forever loop, which will read the command, will do some processing. It may block. It may sometime, in our case, may go outside to a database, may do another service. It will wait. It will make sleep. Do more processing. and it's quite easy. But it doesn't scale because you have to allocate one process per connection. And although Linux is efficient, or other operating systems are efficient for handling multiple processes, and at load that we talk about, like for PayPal and Google and this kind of load, this doesn't scale, doesn't work because it adds up. So the alternative is asynchronous programming, where in this case you have one process handling multiple sockets. In Linux, they are based on a system called ePOL. And in the right side, I have an example. The idea here that you tell this system call to listen to events on multiple sockets, and it wake up when events happen. And typical example, like if you have a listen socket, you have new requests coming in, and you handle creating. In this case, you have a new request coming in, you create a new server. You may have reading for an existing, like imagine that you have like a telnet example. You may have a request from one of the sockets. You can sometimes, you have to do write IO, and because sometimes writing buffers gets full, and when you do write to a socket, it will fail. So what the application will do, basically you have to buffer what's not sent and tell Linux to wake up when there's more room available. Also, you need to handle timers, and of course this must not block, because if you block at any time doing one request, all the other clients will have to incur latency. So, and this is a big restriction actually. So implementation gets complicated, and there are the way it's implemented, there are complex state machines, hard to do, but scalable. So when we had new functional requirements, we had a challenge, right? We could continue adding more features to existing or do something else. And we did. We looked at some options that we have. Also, one of the options was how about writing in Go language? Go language is it comes from Google. It's quite popular in Silicon Valley. A lot of startups are using it. It's supposed to scale efficiently out of the box. The programming is synchronous. You can block. And you basically can create thousands or tens of thousands of light threads, they call it Go routines, in your application. And it's convenient when you write the code. And however, under the covers, Golang library runtime, they take care of scheduling, and they use actually very few operating system threads. Typically one thread per core, per CPU core. So sounds good. I mean, like you have the good of both worlds, right? Easy to program and efficient, scalable. But of course, we're asking, would it work for us? And in particular, what we are concerned about was stop the world garbage collection. So once in a while, Golang and like other garbage collector languages, they have to stop your application completely, and to free some memory, right? They do in parallel some work, but at some point they have to stop the world to do some processing in our case, we cannot handle stop the world for too much time. However, latest versions. So we look at Go earlier, many years back, but we didn't think it would fit our requirements. But latest versions look good. So we decided to try it. And we took a gradual approach. So first we did a proof of concept, and the way we did it here is it's important. If you do a hello world, it's not going to be relevant. So we actually took a most complex feature and we implemented it completely. And we measured performance and look at the code. Does it look right? Is it less how we thought it would look like? And we liked it. Also, doing this gradual approach, we kind of safeguard ourselves. If we don't like it, we just throw away the work. But it's not like writing everything. But we liked it, and we continue. Decided to do the first release with limited functionality and deploy in one of those cases where we don't need all the features. But we also tried on production. Because no matter how good tests we have in development, we also want to see for the production load. We liked it. We continue next phase. We actually implemented everything, but we still had some code that we used from C. Go works very well with C++. So if you, it's actually very easy and quite efficient. And eventually we wrote everything in Go. We were running in production for more than 2 years. It met our requirements, latency and also CPU consumption. All this time, we didn't change the wire protocol, so the client applications were not changed at all. Nobody in the company knew what we were doing. We completely rewrote the server. We had issues and learnings. Since previously we were mostly C++ or Java engineers. And I mentioned earlier we open sourced this. You can take a look. We open sourced with 2 clients so far, Java and Golang. Although this as we open source, it works with Oracle and MySQL. It can work with any database as long as you have a Golang driver for the database, for example, Postgres. I just want to thank my colleagues who worked with me on Hira over the years, software engineers from operations, database administrators. And that's all. Thank you. If you have questions.
Does anyone have questions? Oh.
Thank you for your talk. Did you have any? Do you have any kind of war stories involving debugging Go in production or fighting the runtime or something like that? That you didn't have when you were in C++?
Yes, one of them. Yes, for example, yes, about the scalability. So in theory, right, you can write thousands of Go routines, but under the cover you have only, I don't know, few operating system threads. There was an example where it was not the case. So we noticed that after a certain load, we would see hundreds of threads, and eventually would crash actually. Reason is was if and this is mentioned in the documentations if you look carefully. If Golang is in a system call or is running a C code, the Go routine is allocated to the thread all the time. Now, if you have a lot of routines stuck or talking or in this, it will create more threads. In this case, was actually the C code had a mutex, and yeah, this is one example.
But would you say it's still worth it, the Go rewrite? Was it still worth it versus, I don't know, using like a coroutine library in C++ or?
Say it again, please.
Would you still say that it was worth it to rewrite in Go?
Yes, definitely.
Versus
definitely.
using like a coroutine library in C++?
So I think you need to be aware of this when you run C++. I think, and I think, so this was it was an earlier version of Go, I believe 1.8, 1.9. I think they changed that a bit. So because you can call Go can call C and C can call Go also. And I think they changed that a bit, so you can call C and it will not allocate Go anymore, but still if you go back to C, imagine that you want to use a C library for, which is doing some networking, for example, and you don't want to block. So in this case, you may have to implement some callbacks in Go, which is used by your C code. So you have to be aware of this. And the way what we did actually, the problem got away once we changed. We didn't use C code in this case. Other option would have been you can maybe throttle, or you maybe can limit in your software how many routines using C++ code. Also, it's important. I think some of the Go calls, they may use system calls. Some others may not. For example, and this may not be true for the latest version, but actually it must be. So if you read let's say you read a file. If you read a file, it will do a system call immediately. Now, if you read from a socket, Go optimize this, so they actually don't do a system call every time you read a socket. They optimize it, so and they use epoll.
The network poller, yeah.
Yes, exactly. So they say optimize. So there is not only if you do a read, it will not call a system call. It's optimized. It will put some in some queue, and eventually the net poller will do the epoll for all of the sockets. Yeah, maybe another example I would say, this is interesting. Go has a read-write mutex. So the idea with the read-write mutex is if you have a read-heavy application, you do very few writes, but a lot of reads. So those reads, they don't block each other. It will block only if you do writes, but the reads, they don't block each other. So you scale a lot more than if you have a normal lock, normal mutex. Although this is a little inefficient, some implementations of this read-write mutex, some implementations actually they use two mutexes under the cover. I don't know how Golang is using it. Is implementing it. However, important is that the behavior is different than the read-write mutex in POSIX, if you do it in C. And what they did, they prioritize the writers versus the readers. So now imagine that if one reader blocks or is slow, now a writer wants to write, and now the writer will have to wait until the reader finishes. Now, if you have another reader who wants to read, in POSIX, it will continue. In Go, it will wait for the writer, which waits for the reader. And it was tricky when we found this. Uh, um, yeah.
Thanks.
Let's thank our speaker again. And Patricia will be at the showcase for a bit to answer further questions, but we're going a bit over time now. Okay, thank you. We're now going to pick our winner for the prize. Okay, thank you.
Thank you so much for coming to Patrick's keynote. We're now going to proceed to pick the winner of the prize associated with the keynote. So I'm going to scroll through the people here, the names. If anyone is interested in still trying to win the prize, say now that we'll scan your QR code. So let me proceed to this slowly. Anyone? Okay, thanks for making my life easy. So let's pick a winner now. Congrats. Oh, shit. Can you please go to my coworkers there? Thank you. Thank you so much for coming. The next talk starts in about 10 to 15 minutes, so if you want to come, please join us.
O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude.
Okay, we're a little over 10 seconds away from that landing burn start. Meanwhile, stage 2 continues
Stage
to
2 is
perform
enter
normally.
terminal guidance.
Stage 1 landing burn has started.
All right, let's see what we can see here on the left side of the screen. It's a beautiful day out there.
Landing legs have deployed.
Impact shutdown.
Okay, we were
Stage 2
expecting
FTS is saved.
we were expecting the call out for landing, and we obviously didn't see it there on the drone ship. So let's look back at stage 2.
Newfoundland AOS.
And we clearly did not make the landing this time. However, stage 2, we have confirmed SECO, which is second engine cutoff. Let's listen for the call out of the orbit.
Cape LOS expected.
And we have a good
Nominal orbital
orbit.
insertion of stage 2.
All right, now stage 2 is going to coast in this orbit for a few minutes, and during this time, it'll start to spin along its central axis, which gives the Starlink satellites the momentum that they need to space themselves out over time after they deploy. So we're going to take a really quick break here and then return at T plus 13 minutes and 45 seconds.
Ladies and gentlemen, welcome on stage, Randall Hunt.
All right, what's up, everybody? So what you just saw was SpaceX totally missing a landing, and that's not my fault because I don't work there anymore. But literally, just now, they were launching a Starlink mission, and one of the things that SpaceX does is they launch these cool rockets called the Falcon 9 up into low Earth orbit, sometimes medium Earth orbit, and then they deploy like 60 satellites at once along this little payload fairing and then this little adapter, and then you can see them going across the sky, and they provide internet around the world. It's really, really cool. I used to work there. I don't anymore, so it's not my fault that that rocket did not land. Totally not my code. So what are we here today to learn about? So I want to talk to you about deep learning and kind of this new aspect of deploying code called serverless. There's lots of really funny things you can say about serverless, and I'll get into those later. But I find it difficult to talk about these concepts in abstract ways. I am not an academic. Sorry. I'm much more of a practitioner. I actually dropped out of college. So I dropped out of college. I joined a small startup. While I was in college, I worked at NASA for a while. This startup, MongoDB, I saw it grow from a very small company into a very large company. And then I left MongoDB, and I went to AWS, and then I left AWS, and I went to SpaceX, and I was at SpaceX for a while, and then I came back to AWS. I mostly work in Python. I occasionally use C++. I do a lot of kind of databases stuff. I do a lot of other kind of random things. How many people like JavaScript? OK, so I think that JavaScript is essentially mass psychosis. So JavaScript has taken our industry hostage, and it's forced us into doing things that are unnatural. It's like the dark side of the force. It's very powerful, but very unnatural. So you'll often hear me say very negative things about JavaScript, but you need to know that those negative things that I say about it come from a place of like a love-hate relationship, because JavaScript is important. We need to know it. So even if I dunk on JavaScript all day long, it's not that bad. It's really good. You should learn it. It's a good skill to have in your toolbox. Oh, and if you follow me on Twitter, I don't actually post anything of value. It's mostly just shit posting. So what is AWS? AWS is Amazon Web Services. That's where I work now. We're a global IT solutions provider, and what that means in non-marketing speak is we try to provide resources for compute and for databases and for all manner of other things globally, anywhere, on demand. You pay only for what you use, and it's a really cool way of building new tech. Because if you think about it, if you wanted to start a company 20 years ago, you had to go and co-locate in a data center, or you had to go and buy a bunch of hardware and then shove it into a closet in your office and then hope the office did not burn down. I'm totally not speaking from experience. And then you basically had to get a bunch of T1 lines and plug them in. And that's not your core competency as a business. Your core competency as a business is to build your business. Like, build the thing that you want to build and don't focus on all this hardware. So when you think of cloud, think of AWS. It's very, very big. There's lots of cool stuff. We have 22 regions, 69 availability zones. None of that stuff really matters for what we're going to be talking about today, but I always like showing just the breadth of things that are available. So if you look out here, we can zoom in on an individual availability zone, and you can see this is a fully scaled out availability zone that has many, many different individual data centers in it. Between these data centers, there are 388 unique fiber paths. Has anybody ever had to lay fiber before, like put fiber into the ground, splice fiber? Is it a pleasant experience? It's not. It's a very unpleasant experience. And so we worked with a couple of different companies to figure out how we were going to deal with all these fiber paths. And they were like, oh, you're going to need a truck. And we were like, yes, and? And they were going to like, you're going to need 10 engineers. And we were like, yes, and? And then they were like, you're going to need a giant machine that can dig a tunnel. And we were like, yes, and? And so we did all those things, and we built these data centers, and now we want other people to benefit from them. So why do I work at AWS? I had after SpaceX, I was really fortunate. I could have chosen to work anywhere. I think that AWS has a set of core values that are really, really fun and really, really empowering. And I'm not saying that my career at AWS has been perfect, because it has not by any means. I get in fights with my managers all the time. But I really like the core values. I really like the customer obsession. And one of the things that I use to demonstrate that, this on the left is the fiber optic cable that we used to use. This is a 2-inch conduit. This is the cable we used to use in our metro fiber across our data center back in like 2016. And this has 3,000, 768 fiber pairs. I made up that number, but it's somewhere in that range, between 3,000 and 4,000 fiber pairs. And it's got a nice steel core on it, so as you're going along the ground, you can find it with a metal detector. And that same cord we could have kept using, right? But one of the fundamental things that we do at AWS is we like to dive deep. That's one of our leadership principles. And when we dive deep, that's not saying that we're digging a deeper hole. It's saying that we're really looking into the fundamental properties of how all of this works. So using the exact same 2-inch conduit back in 2019, we were able to put in double the capacity, more than double the capacity in the same amount of space. And to do that, we had to invent a new fiber optic core. We had to invent new technology. We have an applied photonics lab somewhere in a basement in Seattle where people wear goggles and sometimes eye patches if they forgot to wear the goggles. And so this is one of the things that attracts me to working in this company. And I always like to share that. It's not really cogent to the conversation today, but if you want to work somewhere that does this kind of cool stuff across all of the stack, up and down, talk to me afterwards. So what about deep learning? Because that's what we're here to talk about today. How many people already have experience with machine learning? Okay, looks good. So how many people have experience with deep learning? How many people do not know what the difference is? It's okay. Most PhDs still argue about this. No, I'm serious. So when you think about the world of machine learning and compute and the tools that are available for you, you have artificial intelligence. And artificial intelligence is not a thing that exists at all yet. Like it's a fake, it's a bad name for a bunch of math that we do really, really quickly. So if you want to think about it at its core, machine learning, deep learning, all of these things, they are compression algorithms for experience. They are compression algorithms for human intuition or even other kinds of tasks. Think about an MP3. An MP3 is a way you compress music, but it's lossy, right? But you still get it good enough that your brain recognizes what the sound is. Everyone with me? So what machine learning is really doing is it's a lossy compression algorithm for knowledge. It becomes this really, really advanced pattern recognition software that can sometimes learn things through layers of abstraction. But in reality, we're not to the point where it's evolving its own consciousness or anything like that yet. That would be artificial intelligence. And we're not there yet. And I don't think we're going to get there in the next 10 years. But I'm wrong a lot. So when we think about the spectrum of things, if we imagine on this y-axis here, we have compute, right? This is the amount of compute that we have. And then on this x-axis, this is the amount of data we have. So if we have very little compute and very little data, that's called math. We can all do math. This is very simple techniques. We can do this with pen and paper. If we have lots of data but very little compute, that's called unfortunate, because we can't really do anything because we don't have enough compute, so we have all this data for nothing, and this is most Fortune 500 companies. And then if we have a whole lot of compute but not a whole lot of data, this is the realm of something called reinforcement learning. So this is when we don't have enough data to really use all the compute that's at our capacity, whether that data exists or not. Maybe the data just isn't in the format we need, but we can use techniques called reinforcement learning to go in and run scenarios, like fake scenarios. So has anybody played Dota? Defense of the Ancients? It's this really fun game. What about League of Legends? Okay, so if you've ever played one of these games, reinforcement learning is how they teach most of the AIs in these games. And there are other techniques that are used. Sometimes you use reinforcement learning on top of an imperative protocol or an imperative program. But in the end, it's really reinforcement learning that's going to win. And there have been a lot of really cool results recently if you've followed along. So that's one corner of the spectrum. And then over on this spectrum, where you have lots of data and you have lots of compute, that is deep learning. And that's what I want to talk about today. And deep learning used to be fairly inaccessible. There were very few institutions or companies or people that were undertaking this, and that would probably be the 2008 range. And now in 2020, it's very prevalent. Anyone can do deep learning on their laptop if they want to. Don't, because unless it's really, really cold and you need a space heater, that's the only time to run deep learning on your laptop. But so I want to talk to you about a bot that I built called WhereML. And I don't want to take any credit for the original model. So the original work here was actually done by Jae-Young Choi and Kevin Lee at University of Berkeley and the International Computer Science Institute. They built something called the Location Net. And even their work is based on another model that was built at Google called Planet by Whalen et al. And I'll be talking a little bit more about that later. But if you want to try this, what it does is you tweet a picture. Does everybody use Twitter? Do I still count as a millennial? I don't know. What is this generation? Anyway, you tweet a picture, and then it'll reply with the place in the world it thinks that picture was taken. And it does this using only the pixels in the image. So using only the data in the image, it will guess where in the world that picture was taken. And this is a network that we can build and we can train and we can modify, do all kinds of good fun things with it. And if anybody wanted to try it, let me know the results. So feel free at any point in time to interrupt me, post any picture from your camera, post any picture that is appropriate, and then tell me if it got it right. And if it got it wrong, just shut up. So how does this all work? Well, Twitter has something called the Account Activity API, and the Account Activity API is powered by webhooks. What that means is I, having my server or my endpoint, am able to go over to Twitter and say, hey, Twitter, I want you to send me an HTTP request every single time this type of event comes in, and then my server processes it. In this case, my server is an Amazon API gateway, which invokes an AWS Lambda function. You can tell it's an Amazon product because we put our name in front of it. And then we keep invoking subsequent services, and then we get the result back, and then we post it back to Twitter. And I'll go into more detail about this later, but first I wanted to talk a little bit more about deep learning and machine learning and how it's being used these days. So we are using deep learning to solve some of the hardest problems in computer science, from self-driving cars to, has anybody used Snapchat? Yeah. So you know on Snapchat how they make your face look pretty? Like, that's deep learning. So really just fundamental stuff here. We're also using it in oncology, so we're using it to look for breast cancers and to look for all kinds of other abnormalities in different medical imaging. So it's got a whole spectrum of things that it can be used for. Some of them terrifying, some of them really exciting. And if you look at the rise of artificial intelligence over the last 60 years and the terms that have been used, there's really been a sharp increase, and it's only going up. So it behooves you as students and as academics to really become practitioners in this space. You don't necessarily have to use it in your career, but it's like calculus. You have it in your back pocket if you ever have to, I don't even remember what calculus does, to be honest. I haven't used it in so long. If you ever have to do some integration, you can go into Wolfram Alpha. Or you know what I'm saying. You want to have this tool in your pocket so that you can pull it out and bring it to bear on a problem that you might face in your career. And then for those of you who are really interested in it, you can pursue it as a career because it's a very, very broad set of things that you can do. And artificial intelligence, it really starts back in 1957. Frank Rosenblatt builds this machine. When I say he builds the machine, it was mostly graduate students. Any graduate students in the house? All right, they're too busy actually working. So the graduate students basically took this machine of photosensitive cells, wired them all up, and then you could show a card. This is in 1957. You could show a card to these photosensitive cells that said the number 1 or the number 2 or the number 3, and then a little light bulb would show up on the computer, and it would say, hey, this is the number 3. And I'm going to show you how you can write that network yourself in modern times, like in JavaScript if you want, on a computer. And then I want you to imagine how many hours the graduate students spent training that network by hand. And then, this technique, this perceptron, this is kind of around for a while. In 1975, Paul Verbos comes around and he invents this algorithm called backpropagation. And he doesn't really invent it. It's like a rediscovery of a known algorithm. And this is the ability to, as you're training, did it get it right? No? I told you not to say anything. OK. Did anybody post it and it got it right? Yes. 1 out of 2 people. Yeah, so 50%. We're doing it 50% here. All right, so 1975 comes along. Paul Verbos has this backpropagation algorithm. And what backpropagation does is it says, as we get along in this network, what we can do is we can calculate the epsilon, the error, between our expected result and our desired result, or our desired result and our given result. And then we can propagate that error backwards and adjust the weights and balances in the network such that we start getting better and better results. And then lots of other things happen, and then there are a bunch of people who get ignored by academics for many years because reasons. And then 2008 comes along, and then deep learning is back in style, and then there are these people who used to go and want to talk about deep learning at academic conferences, and they would be like, oh, no, we don't want to listen to you. That's not how artificial intelligence works. The imperative model is the only way to go. And then all those people are now keynote speakers, and they jump up on stage, and they pop up like double middle fingers to all of the people who kept them down for so many years. So really, really fun academic society. So where do we use deep learning? So at Amazon, we have this company called Amazon Robotics. This is where we have a couple of different technologies running in concert. So you'll see there's an individual machine learning network that's running on the robot itself. This is responsible for dealing with the sensor fusion of, where do I move? What am I supposed to do? Am I about to run into something? How do I adjust? All this other stuff. Then you have other networks. So there are networks that are joined into cells across not just individual warehouses, but even across the entire planet of all the different warehouses that are aware of the different products and know how they might need to move around and all kinds of other things that they might need to do. There are other fun things that we can do where we can program drones. And these drones can use a set of deep learning technologies to do everything from plot their flight path, file their flight path with an aviation authority, fly the flight path, and then avoid obstacles along the way. And this is probably how we might deliver things one day. But the really fun thing is there's this store in Seattle where you can walk in and you basically steal a bunch of stuff. And I don't know if everyone else gets a thrill from shoplifting, but it's just been my dream my entire life, but I've been too much of a wimp to ever undertake it. So this store, you swipe your phone when you go in, you're just moseying around, and you're just like putting stuff in your pockets, and then you kind of like leave the store, and you just go. And there's no checkout, there's nothing like that. So how does this work? So there are a series of cameras, there's a series of RFID sensors that exist throughout the entire store, and they track everything that you're doing, which is kind of dystopian. But beyond that, it's really, really cool because you can just walk out after you've stolen a bunch of stuff. I'm just going to skip ahead here to show you a terrible mistake. So once you get a cupcake, under no circumstances should you ever put that cupcake back. Luckily, she did the right thing. All right, so these are the things that we use machine learning for and deep learning for. What our mission is with machine learning and deep learning is to actually put these tools into the hands of as many developers as possible. Whether you're a developer in your garage, in her dorm room or your office, or like his or her attic, wherever you are, you should be able to take advantage of these tools because they used to be locked into the hands of these Fortune 500 companies or even Fortune 5 companies that had billion-dollar budgets to throw at these problems. And most of these problems were really boring things, like how can I get 1% more ads clicked on? It's the most boring problem in the entire world. I have zero desire to worry about ads. So we have lots of different customers that are doing this. I'm very fortunate I get to work with a lot of these. And we'd like to think about machine learning at AWS in a couple of different tiers. So in the bottom tier, you have things like your frameworks. So how many people have used TensorFlow? Right? How many people have used PyTorch? Okay. How many people like PyTorch better than TensorFlow? Just for the purposes of any video, that was 100% of the audience. Everyone drastically prefers PyTorch. It's the best. Totally not my own personal bias at all. So then you have things like Keras, you have other frameworks, and then this is where I would say only 10% of the machine learning users will spend their time, right? Only 10% of people will end up touching this level of the infrastructure. One level up, where you're using these frameworks, where you're consuming these frameworks and building stuff on top of these frameworks, that's where most people will spend their time. Well, maybe not even most, maybe like another 50%. And then the rest will spend their time building services on top of APIs that are powered by machine learning. So SageMaker is one of the services that I'm not supposed to say is my favorite thing because we're not supposed to have favorites, but no one from Amazon Legal or PR is here, so I'm just going to say SageMaker is by far my favorite service. Hands down, it's the best. I love it. Thank you, SageMaker team. And we're going to talk a little bit more about what it does now. But before that, let's talk about what machine learning is. So again, everybody raise your hand if you've heard of MNIST. All right, MNIST is this. It is a set of numbers that are handwritten numbers, 28 pixels by 28 pixels. And what you do is you can recognize the handwritten digits. Now, there are other kinds of cool, fun, new data sets, like CFAR, which is like recognizing different items of clothing. But this one is known and understood. And what we're going to do is we're going to walk through how all of this works. Now, the animations that I'm about to show you are from someone named 3Blue1Brown. They have a YouTube channel, or he has a YouTube channel that is phenomenal. And if you wanted to skip the rest of your college education and become equally as intelligent as all of the PhDs, or equally as informed, perhaps, as all of the PhDs that you're talking to, go to this channel, watch all of the YouTube videos, and you can skip the rest of college. Do you have to pay for tuition here? Yes? OK. Well, in the States, this is a much more valid thing, because tuition costs a lot. So we're going to talk about how we recognize these numbers. So we take our 28 pixels by our 28 pixels, This gives us 784 weights. This gives us 784 values. And then we're going to say, of these 784 values, we're going to connect each one to a smaller layer. This is going to be our hidden layer, our first hidden layer. This is our input layer. This is our first hidden layer. All of the nodes are fully connected, which means every node in this layer is connected to every node in that layer. These are different weights and biases. We're going to add a second hidden layer, and then we're going to have an output layer. The output layer is going to be the digits 0 through 9. And this output layer is essentially our whether or not we got the question right. So we know what some of those digits are labeled as, right? So we know that some of them are 0, 9, 7, da-da-da-da. The goal of machine learning is to take a topology, a network topology like this, and to figure out what the correct weight and activation function for each of these lines, these edges, is. And by doing that, you are essentially teaching the computer to recognize these things. Now, there's a danger. You can overfit. And overfitting is when you really are just a compression algorithm. You've memorized the entire set of data that's given, but you can no longer generalize. So when you overfit, that's when you've taken in the entire training set of data, and you've just memorized what the right answers are. How many people have passed exams this way? Yeah, I'm with you. So when you do this, you're no longer able to really build out and expand into new problem sets that are given to you. And this is a common problem in certain machine learning and deep learning workloads, is that you overfit to the set of data that you've been given. So what do? What you do is you take a portion of the data and you make sure the network never sees it during the training process. And then you can replay that portion of data that you know to have a correct answer, and then use that to tell you whether or not the network has learned and generalized the things that it needs to learn. So what is the network doing exactly? Well, in the interest of time, I might skip along here. So what is the network doing a little here? Is it maybe this layer, this is number 9, so we're going to split this out, we're going to send it through. Maybe this is saying, okay, well, the number 9 is going to be made out of these little edges. It's going to do like convolutions to detect where the edges are. And then we know if we have a long line and a little loopity-loop, that corresponds to a number 9. So the question is the network doing this? Sometimes yes, sometimes no. It turns out the way that we as humans learn to recognize things is not necessarily the most efficient or the best way, or even an equally efficient way of recognizing numbers. So even though we might see numbers this way, there are other algorithms that exist in the space of, like the dimensional space, that have equally performant values. And this is a really cool aspect. So as you're training these deep learning networks, one of the things that you often do is you will keep the artifacts around. So you will keep different trained artifacts and weights and values around, and store them off to the side, because maybe you've reached a local minima or a local maxima, and you're like, okay, well, in order to get out of this, I need to train for another 2 hours and then crawl out of this space and then maybe reach another space. There are lots of little good theories on this, and I'm too dumb to understand them. So how does this work in practice? So in practice, you'll have a business problem, and the business problem is often an executive went to a conference and learned what machine learning was and has decided that this is now what they want the company to do. They don't have any other actual plan in place. And then they're like, cool, let's do machine learning. So they hire a bunch of machine learning people, or interns as they're most often called. And then they tell the interns, hey, here is the problem that we want to solve with machine learning. Doesn't matter whether or not that problem is actually possibly solvable by machine learning or not. And then this is the data that we have or don't have. And we want to collect this data. We want to prepare the data. We want to get it into shape. And then this is the most important step, actually. So if I were to give you a set of 13,000 numbers and say find the outliers, how many people would do that? No problem at all. 13,000 numbers, find the outliers just by scrolling through. Okay? It is not possible for a human being to do that. So what do? You plot them. So one of the most important steps and one of the most underrated things that you can do in data science and machine learning is actually plotting the values, building them out, figuring out where they need to go. And by doing this, you will be able to rip out all of the stupid values in your data. And this is one of the most important steps. So do this, and then you can do feature engineering. Feature engineering is where you bring that good old human noggin in to say, actually, this is a really dumb thing for the computer to consider. And then you can do model parameter and tuning, and then model evaluation. These last two steps are almost entirely automated at this point. Almost everyone uses TensorFlow or PyTorch or Keras or whatever to go and run those steps. You can use a naive Bayesian classifier to go and say, hey, just run hundreds of different jobs and then close the ones that aren't converging. And then are the business goals met? And of course, the answer is no, because you started with a bad problem because it was an executive. And then a developer comes along, and a developer says, hey, why don't we do it this way? And then the developer goes and makes a real problem and a real solvable thing. And then the business goals are met, and you augment the features, and then you go and you deploy. Now, how many people have deployed something to prod before? It's the only way to deploy. So when you deploy to production, you constantly have to monitor certain things, whether it's CPU or memory or U-limits, or you have all of these different terms and tools that you're using to track what you've deployed. So one of the things that we do with machine learning models is we're monitoring all of that, but we're also monitoring the effectiveness of our predictions. And this is a very important step that most people forget. And if you don't believe me, has anybody ever tried using autocorrect on their iPhone? So this is what happens when you don't have this line, where you don't measure how many times someone rejects the autocorrection, and you just keep suggesting the same autocorrection so that hello becomes, I don't know, Hodor, whatever the correct response is. So it's really important with machine learning to not just deploy the model out into the wild and say, OK, everything's good, we're done now. You also want to make sure that you're really following along and making sure the predictions that it's giving are correct. So there are lots of different tools within AWS for using all of these things. SageMaker makes it very easy. And I'm going to kind of skip over the gross majority of the marketing material and try and get into the fun parts. But what SageMaker allows you to do is you have a Jupyter Notebook environment. You have a bunch of built-in algorithms that we're not going to talk about today. You have an ML training service. This is just automated training where you can do parameter tuning and things like that. And then you can host the model and do that retraining that I was talking about. OK. So like I said, skipping over lots of the marketing stuff. Lots of marketing. Here is something that I used when building this model. So I'm sorry, I feel like you're all blinded by the light. So I'll get over this slide very quickly. Open data on AWS. This is a GitHub repo that you can go and visit. Oh, boy. I'm sorry. Go to this GitHub place. Here it is, registry.opendata.aws. You can add in your own data sets. There are lots of very, very cool data sets. You can even augment the existing data sets by using an army of humans to go and label all the data and do good stuff. Here are a couple I'm going to talk about. The Multimedia Commons data set is from Flickr, so it's, I think, 100 million images and videos from Flickr that are Creative Commons licensed that you can use. They have all their EXIF data. They have all kinds of good stuff. This is really, really useful for doing different kinds of machine learning workloads. There are workloads that have sustainability stuff, so things like the ocean mapping, the Arctic ice mapping, all kinds of good stuff like that. Imaging of mosquito populations and things like that. All of the data from the Hubble Space Telescope. The 1,000 genomes data set, the OpenStreetMap data set, lots and lots and lots and lots of data. And most of this stuff is hosted for free. And if you have a data set that you would like for us to host for free, reach out. So how do we build WhereML? What do we do? The first thing that we do is we take MXNet. This is a framework. How many people have ever used MXNet? So MXNet is very similar to something like TensorFlow or PyTorch. It's a framework for doing machine learning. And what it does that is very common in a lot of other frameworks as well is it separates the data and the computation. So it uses a symbolic math notation in order to define the topology of the network. And then from there, you forward data through the network in order to accomplish things. So this was trained with 33.9 million images that have their EXIF data in them. EXIF data is data like what was the what camera was used for taking this picture, what were the latitude and longitude coordinates when this picture was taken, what was the exposure settings, what were all of these settings. And then we use Google's S2 spherical geometry library to go over and build out a cellular architecture of all of the different possible outputs, and I'll show you a little bit more what that looks like in a second. And then we built it all on the ResNet 101 architecture. ResNet is a little network. I'll just show it to you, because obviously I don't need to explain this. This makes perfect sense, right? Perfect, yeah. So moving on. No, what ResNet does is one of the problems in deep learning networks is the deeper you go, the more problem you have with back propagation. So the more problem you have getting the epsilon error from that original calculation all the way back further, closer up to the front of the network. And one of the issues that ResNet solves is it makes the network a little bit wider by basically sending residual copies of the data through the network in order to broaden, like make it wider, and it's almost like a cheat code. So this is a drastic oversimplification of what it does, but if a signal is strong enough in any particular area of the network, you can basically imagine that signal propagating through much faster than it would if it were just going through the network without any of these residual copies. None of that's important because I didn't understand it when I started this. I still don't really understand it. I just copy what the academic papers say. But regardless of me not understanding it, I was still able to make use of it. So this is what the multi-scale partitioning layer looks like. So you can see in places like London, we have many, many more cells than in places like the Antarctic Ocean or the parts of the Pacific Ocean that have no islands or anything. So there are very cool values that you can do. And this is all built on top of something called a Hilbert curve. So a Hilbert curve is a piece of fractal geometry that preserves locality across the xy coordinate plane. So as numbers get closer together on this line, they are also close together in the Cartesian plane. And that's how you can use a Hilbert curve to generate these sparse maps where the cells are very densely located. And you can use this across all of computer science. Like if you're having trouble with something, if you're having geometry problems, son, I got 99. I don't remember how it goes. But anyway, use this when in doubt, because it applies to everything. The more that I exist on this earth, the more that I find this thing just exists everywhere. All right, so what are the pros of this approach? So it is surprisingly precise in cities that have a large number of partitions. So in Paris, it will tell you not just you were in Paris, it will tell you what side of the street in Paris you were on. Dystopian future, here we come. It's extremely fast inference. So the entire network is only 300 megabytes, which means you can forward stuff through the network very, very quickly. So if it fits in RAM, you're talking 60 CPU ticks before you get your result, right? So you go boom, 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 propagate through, and now you have these giant, these giant chips from AMD that have these L1 caches that are a gig. Has anybody seen that? It's just unreal. These are giant, giant chips. They cost $25,000, but man, can you imagine playing Crysis on that? Anyway, or Minecraft, just Minecraft. All right, so we get excellent performance for unique objects and landmarks. The cons are that it is surprisingly poor at really common things. So I don't know if 7-Eleven uses the same light bulbs everywhere in the world, but you take a picture of a 7-Eleven sign, and it will tell you with equal confidence that it's in Japan and Texas. It's just and McDonald's signs too. So McDonald's signs, 7-Eleven signs, if you ever want to fool the network, just wear a McDonald's sign on your face. I'm sure McDonald's would pay you. All right. And it's very inaccurate in places that don't have a lot of cells for obvious reasons. So this is based on Planet. So the Planet work was done. It took, I think, 2.5 months to train. This took 9 days to train. In subsequent iterations, we were able to get down to 4 hours of training time. It used a very, very big data set over on the Planet side. The resulting model was 40 gigs. And then the performance is quite a bit better on the LocationNet side as opposed to on the Planet side. So how does the infrastructure work? We have a Twitter webhook that calls out to API Gateway. This is what API Gateway is. That API Gateway will invoke a Lambda function. That Lambda function calls out to SageMaker. SageMaker does the inference. It forwards the stuff through the model. And then Lambda posts the results back to Twitter. So this is what a proxy invocation looks like. We have the client, which is Twitter, coming in, telling us to talk over there to that Lambda function on the far end, and then we send it back. So let's look at what this looks like. If the path matches, all good. If it doesn't, we return. Then we need to make sure that we're doing our challenge response check correctly. So this is just security stuff. Moving on past all of that, moving on past all of this, we can get into the fun stuff. So now we know that the request is valid, right? The request is good. So for each of the tweet create events, we want to validate the record, which means I'm not responding to myself. If you ever want to get banned from Twitter, just make a bot that constantly responds to itself. Totally not talking from experience. And then you call out to this endpoint, and then you add some emojis in for the millennials. This is where the fun happens. So this is what the SageMaker architecture looks like. We have the model loaded in /op/models, and then we have a little Flask application. This is a Docker container that responds to /ping and /invocations. So this is what the inference code is. We're going to import MXNet. We're going to bind the MXNet model to the CPU. We don't have to bind it to the GPU because we're not going to be doing any training. We're just going to be doing inferences. If we were training, we would want to bind to the GPU because there's an advantage to sending very high bandwidth items that are going to be working for a little while over to the GPU because it's more efficient. But this is just one thing that we're forwarding through the network. We're going to use the ResNet size. So this is 3 channels. It's going to be 224 pixels by 224 pixels. We're going to create a batch. We're going to load in that grids file. That grids file is that thing that we pointed to earlier. And then from that grids file, if you take nothing else away from this presentation, Unicode is really stupid. So the way that Unicode works, if you add this offset to any country code, you will get the emoji flag of that country. So I have no idea how this happened. I went on Stack Overflow to figure out how this worked, and the answer was my own from like 3 years ago. So I don't know who discovered this or who built it this way. If anybody does know, I simultaneously want to hug and slap that person. But this is really, really cool. So this is the offset. You add it to any country code like Great Britain. What is the country code for Portugal? PT? So you add it to PT, and you'll get the Portuguese flag. And yeah. Just a little interlude. So now we're ready to do predictions. So how do we do the predictions? We say mod.forward. We have our module. We say forward. We sort the results by the probability, the confidence score, and then we return the number of predictions that we want to return. And then we have the best health check ever. We return an empty 200 OK regardless of the state of the application, because if something's wrong, then that won't work. But if something's wrong but not wrong enough, then it will work, and we'll just blindly send invocations to the application anyway. This is called production. And then we go and we call predict. This is the entire Docker file. We install a couple things. We throw it on port 8080, and that's it. So Twitter, is Tracy here? All right, well, Twitter is wonderful and terrible at the same time. I would say today, Twitter is much better than it was in 2016 when I was first working on this, when all of this stuff was in beta. So rather than dunk on Twitter, I feel like a lot of my criticisms of Twitter are no longer valid. But just know, even when you're a giant company like Twitter, you can still make really bad mistakes with APIs. Excuse me. So this is how it works. You basically go and you say, this is the webhook that I want to talk to. And of course, all the endpoints end in .json because that makes sense. And then this is just a stupid example architecture that doesn't really matter. I want to end on a kind of like positive note that is, I am not a machine learning expert. I have learned a lot about machine learning over the last few years, but everything that you saw just now was live coded on Twitch. So I run a Twitch channel, twitch.tv/AWS. We grew it from like 0 to 7 million followers or viewers, and it's a lot of fun. Go check it out. We do live coding all the time. I mostly don't do anything now because I'm just kind of sitting back and like sipping my champagne, watching the dollars roll. No, I'm just teasing. This is like, if you go to the PyTorch homepage, right? Like it talks about Jacobian vector matrices. And I don't know about you, but when I read that stuff, I get freaked out. Okay? Like I don't want to hear the word Jacobian. Okay? Like I don't want to see integrals. I don't want to see matrices. I like use plain English. So if you can like surrender control to your baser instinct of fear that I have of math, and just kind of push that aside and look at like the way different people are using things, you can piece together an intuition for how all of this works. And eventually, you'll come back to like Jacobian matrices and it'll be like, oh, cool, that's how those work. Like, this is fun. I'm glad I learned this. So don't be afraid of machine learning. It is really easy to get cool stuff built on top of it. Thank you so much for your time. Feel free to shoot me an email, and I'll be up there for questions later. Thanks, everybody. Yeah.
Any questions, guys? No questions for Randall? I don't think I'm blind, so thank you so much, and give a warm round of applause for Randall again, please.
Olha, pá, se quiseres fica com o micro.
Hi guys, we're just going to pick the winner for this session. My colleague will show the names that are in the race right now. Well, just let us know if you're not in here, okay?
Rocha. Evitar pessoas que... Mas estavas cá. Eu estava cá na talk. Não, tu estavas. Sim, mas ela está aqui. Eu estou a falar para o rapaz de atrás. Eu não quero que nada. Então, já está. Desculpa, enganei. I'm going to select the winner now. We're sorry for this small problem. Diogo Nogueira. Okay. Can you go pick up your prize in the showcase area? It's on the exit of the auditorium. On the left, please. Thank you so much for coming to Randall Hunt's talk. The next keynote will start in an hour and a half. Again, we're very sorry that Bhairav Mehta had to cancel his talk. So we're going to catch up now at 5:30 with Stephanie Zosta's keynote. So see you there. Thank you. Até o PC de métrica. Não sei. Ai. I'll ask for everyone to leave the auditorium, please.
O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude. nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everest, o futuro é teu. Traz a tua atitude.
Ladies and gentlemen, welcome on stage, Stephanie Seto.
Hello? Okay, cool. Hi everyone, hola. My name is Stephanie. I am a product manager at Airbnb. Excuse me. And I specifically work on building mobile development tools. In a previous life, I used to work at Facebook, where I was a technical program manager for a couple years, working in a very similar space on developer infrastructure. And today, I will be talking to you all about building for mobile, lessons and stories from the very early stages of mobile all the way to current day. Can I get my deck on the screen, please? Cool, awesome. So with that said, let's get into it. As far as how our time together is going to go today, we will first cover a little bit more about the evolution of mobile as a major computing platform. And then from there, we'll go and actually deep dive into a couple of different companies I've gotten the chance to get to know a little bit better and talk about how both of them have actually been able to deal with and address and answer this mobile question and challenge and opportunity. So with that, let's get into it. A little brief history lesson, talking a little bit more about mobile. So when we think about the very early stages of mobile, right, it all started with the very first mobile phone. This was the Motorola Dynatec 8000X. It was the very first mobile phone that was ever created. It was launched in earlier than some of us might think, in 1983. And at the time, as you can see, it was basically the size of a brick. You could only talk on it for around 30 minutes before its battery inevitably died. And it also cost $4,000, which, you know, in inflation-adjusted terms is probably even much more than that now. So by today's standards, that's not very impressive, right? 30 minutes, what can that really get you? But at the time, this was considered hugely revolutionary, right? This was the very first time you could make a call to anywhere in the world without needing to be tethered to a landline, to a device, without needing specific wires to actually make this call. And so this was actually considered a widely successful phone where there were thousands of people that were on the waiting list to buy this. And so ever since then, ever since 1983 when this was first launched, hardware for mobile devices has continued to evolve over time, where devices have gotten from the point of being the size of a brick to something that has grown smaller and smaller to the point where these phones can now fit within our pockets. In addition to that, these phones have also added much more processing power, right? Which have also enabled us to do all sorts of functionality and capabilities that we would never have imagined many years ago. And so some interesting notable milestones on the evolution of mobile devices and hardware. There's this really popular Nokia model, which was extremely popular in the early 2000s. And then, of course, there's the iPhone, which we can never forget, which was not the very first smartphone by any means, but did represent a huge revolutionary breakthrough when it came to touch controls and inputs on a mobile device. Prior to this, phones were, for the most part, you only interface with them through buttons, through a keypad, and that really limited how you're able to interface with apps, with the internet, with your phone as a whole. And instead, with the iPhone, you get this full-screen, beautiful touchscreen for the very first time, which allows you to unlock a world of possibilities that are now possible on a mobile device because you now can interface with it in a much more granular, specific way. And so from here on out, I think we're much more familiar with the evolution that happened after the iPhone was launched. Obviously phones have continued to get thinner and thinner. Screens have gotten larger and larger. It almost sometimes feels like things have gone all the way back around again, where, we had flip phones way back in the day, and we see manufacturers actually starting to do flip phones with touch screens and all kinds of crazy things like that. And so in the meantime, as this hardware evolution is happening, there's a very parallel software fight that is happening at the same time across and between all these different major tech players that all want a piece of this mobile software pie. Everyone wants a chance to own and operate the next major software computing platform. And so even though now, right, we're here in 2020, these fights are largely over, we have a pretty good sense of who has won. Way back when, 10 years ago, that fight and that outcome of that fight was not clear at all. There were all these different players that were trying to, get a stake in this, and we'll cover some of the casualties along the way. Some of you might have remembered, but maybe not, in the early 2000s, Microsoft actually lobbied really hard to get a seat at the table and really make a stand when it came to the different mobile platforms out there. They did so with the second iteration of their mobile platform, which was called Windows Phone. But the challenge that they ran into, that all platforms inevitably run into, is trying to build up that initial traction to get that platform going in the first place. The thing with platforms is that they're ultimately two-sided networks, right? Two-sided ecosystems where you have developers who actually work to create and write the apps for the platform on one hand, and then you also have users who are actually going to use the platform on the other hand. The challenging thing, though, that we run into is that oftentimes these groups don't want to move without the other one being there first. And so hence you run into this really challenging chicken and egg problem where you need one party to go first, but no one wants to go, and it's hard to actually really get that started. And so oftentimes, developers specifically, though, they want to make sure that there's going to be a stable, large enough, healthy enough user base of users to make sure that they're going to get a return on the investment they're going to make by building this app. And then on the other hand, users also want to make sure that there is a healthy, vibrant app ecosystem, so they can make sure that if they're going to make that leap of faith and switch platforms, they can actually from there on out, make sure that they have all the apps and all the functionality that they want to do on their phone. So the issue that Microsoft ran into, that many people have since run into, is that they were really unable to, even despite all the investments that they made, all the partnerships that they made with companies to create apps and things like that, they were really unable to get that momentum going such that they could really get this platform off the ground. And so as a result, 5 years ago in 2015, Microsoft ended up pulling the plug on Windows Phone, and it no longer exists. On a similar note, Amazon also tried a really similar play around trying to push into the mobile space by launching a specific phone and then also an operating system on top of that. This came in the form of the Fire Phone and the Fire OS, which was a fork off of AOSP, or the Android open source project. But unfortunately, similar to Microsoft, they also ran into similar issues, were not able to get their platform off the ground, and a few months after they launched this effort, that also ended up folding. And so that brings us to the modern day and the winners that we are ultimately right now much more intimately familiar with. Of course, we have iOS from Apple, we have Android from Google, and this has lent itself to this really interesting duopoly and this really interesting set of dynamics that have formed in the mobile space. Of course, we have iOS, right, that has clearly dominated the high end of the market. They have a very small but much more influential, affluential user base of users, whereas Android, on the other hand, has essentially captured the remaining 75% of this market. This has, and basically captured everything else that's left. This has also resulted in a very interesting set of approaches when it comes to monetization as to business models, where iOS on one hand and Apple, they actually end up making most of their money off of the margins that they get from selling iPhones and related accessories like AirPods and things like that, and then also in taking a cut of App Store transactions that happen. On the other side, Android and Google have decided to go in another direction where they're really going much more for scale, right? They want to get as many people using as many of their properties, as many of their services as possible so that they can leverage that data, that attention, and actually use it to sell ads against. So that is effectively where we see ourselves in the modern day. This is the mobile landscape as we see it. This is sort of how it's played out. And we next will go and deep dive a little bit more in talking about one specific company, in this case Facebook, to talk a little bit more about how they dealt with the emergence of mobile as a major computing platform and how they responded to that. So it starts with sort of the strategic approach. Way back when, if we rewind and go back to the days of those mobile software wars, it turns out Facebook actually also tried to put its hat into the ring and see if it could also own and manage a software platform. They did so by taking a page out of the Amazon playbook, and they did something very similar where they launched a software and device at the same time in the form of Facebook Home, and then also partnering with HTC to create the HTC First, which is known as the Facebook phone. The idea here was that this was a mid-range stock Android device. It had this Facebook UI skin on top, and the general hypothesis here was that effectively they were thinking that, okay, we'll have these very tight social integrations with Facebook. You have all this social functionality that's baked straight into the phone itself, and we think this will differentiate this phone relative to all the other offerings out there on the market. However, by the fact that many of you probably don't know that this exists or ever existed, and the fact that this no longer exists, it clearly it goes to show that that hypothesis was incorrect, and that when the phone was actually launched, it actually came out to pretty poor reception. There was a lot of feedback around poor performance and the specs of the phone just really not being up to par. And so as a result, Facebook ended up, shortly after launching this, 6 months after launch in 2013, it also ended up killing this particular project. One small note though, one silver lining that did come from this project was the chat heads feature. If you use Android, you might have seen the chat heads feature where there are these little bubbles that show up that you can use that actually overlay on top of the OS and all the other functionality that you might be using. This actually originated from the Facebook home days, so there was some degree of innovation that did come out of this experiment. And so, yes, unfortunately, it was dead. The next phase of the Facebook mobile journey then continues with something called the Facebook Creativity Labs. So this was an internal incubator that was started up in 2013. And the idea here was that there was this trend at the time where many companies were going towards the direction of building out app constellations. These are effectively suites of custom apps that are created to help solve for very specific workflows, with the idea that the thinking was at the time was that apps were starting to get very large, very monolithic, and to the point where it was very difficult for users to figure out how to navigate through these apps and actually do what they need to get done. And instead, many companies were erring towards the sides of breaking up their apps, creating smaller subset apps that would then solve very specific workflows in and of themselves. And so Facebook very much so took a page out of that playbook, and they launched a number of different apps in a number of different categories. Most notably, this included Paper. Some of you might have heard about this. This was a news reader app that essentially would pull all the stories from your newsfeed, combine it and curate it with a number of different highly ranked stories, and then show them to you in this newsreader app. This actually pushed the envelope quite a bit from a design perspective, and there's actually many parts from Paper that we actually still have technology-wise in the main Facebook app today, as far as the way we display notes, the way we do instant articles. And so that was Paper. And then in addition to that, there also were apps like Rooms, for example. This was an anonymous chat room app, sort of akin to Secret, which some of you might have heard of from a couple years ago, and also Blind, which is a very similar sort of secret social network that is entirely anonymous that still exists to this day. And then lastly, there is also Riffs, which was more of a tool that people could use to actually build collaborative social video. And this is just a small sampling of all the apps that were created during this period. However, by the fact that most of these apps also no longer exist, many of you probably don't know about them or recognize them, many of these apps just also did not find a large enough user base. And shortly after, a couple years after this incubator was launched in 2015, we also ended up shutting this down. And so lastly, as all these different phases of evolution are happening, right, we're experimenting with the phone, we're experimenting with these app constellations and these specific apps. Meanwhile, Facebook continues to do a series of really key acquisitions throughout the decade. It starts with Beluga, which it actually ended up being the foundation for what is currently now Messenger in 2011. And then a year after, there was the acquisition of Instagram, really famously for $1 billion. And then a couple years after that, there was WhatsApp, of course, which made an even bigger splash in 2014 when it was acquired for $19 billion. And so when we think about the Facebook surfaces on the whole today, right, it did not end up being a number of these different things. It did not end up being a phone platform, right, as much as Facebook has wanted to own a platform for a really long time. It did not end up as the set of app constellations and these very hyper-specific custom apps. And it also did not turn out to be one large monolithic app where everything was bundled all in one thing together, sort of similar to the way we see WeChat these days in China. But instead, Facebook has sort of fallen into some place in the middle of that spectrum where they now actually have a very core set of key surfaces and apps that serve very specific functionality. And Facebook now refers to these apps as a sort of core family of apps. So that brings us to our current day and the major surfaces that we are familiar with. We'll now sort of take a pivot away from the sort of strategic side of things and talk a little bit more about the technical architecture and the major frameworks that the major Facebook app has used. And so to start from the very beginning, 8 years ago in 2012 when these were first launched, the company at the time made a very large, very public bet on HTML5 as the vehicle that they would deliver these apps through. Coming from web, I think it was a very natural decision and a very natural path to go down, because coming from a web-based world, they saw the promise and the lure of cross-platform and all the benefits that would come with it. Of course, the ability to write code once and run that everywhere, and then also, in addition to that, there is also a lot of draw around being able to decouple the app, the release cycle, right, from the native mobile release cycle, so that they would instead rely a little bit more on how you end up pushing web code, where you deploy your code and users can start using it right away. This runs extremely counter to the way mobile releases code, which is quite different, where there's a lot more friction from the point at which you submit your code and you want it to go out, and to the point where users actually start using it, because there are many steps that need to happen along the way. Of course, you need to package your app, you need to submit it to the App Store, you need to get it approved by the App Store, which can take a couple days, and then even from there, the user actually has to then go request that, download that, and actually install that code before it can start running, which can be in the order of weeks, if at all ever. And so there are all these benefits to cross-platform that the company really liked, but at the same time, there are also downsides to this, of course, as there are with anything. One major downside that we see with HTML5 sometimes, and with cross-platform specifically, is that oftentimes when you architect your code in this way, it can lead to these performance and user experience issues, because you are working through this intermediate framework, right, instead of working with the underlying native components themselves. And so ultimately, this was the issue that these Facebook HTML5 apps ultimately ran into, where they ran into a whole host of performance issues and user experience issues that they had a lot of trouble debugging and working through. From one particular notable place where they really suffered was around the area of scrolling performance, where ultimately, when you dig into this specific space, what you end up finding is that in order to have really good scroll perf on one given platform, oftentimes you have to do a lot of tuning and optimizations for that platform specifically and the parameters that are there on that particular platform itself. And so when you're working in this very cross-platform world, oftentimes that approach ends up falling down, because the more you optimize for one platform, it ends up resulting in a suboptimal or non-fluid experience for all the other platforms that code is running on. And so with that, Mark Zuckerberg admits a couple months into this particular project that they bet too much on HTML5 and that it ultimately was not going to work if they were going to really invest a lot in mobile. And so as a result, shortly after, later in 2012, the company really starts to really fully commit to building up these native Android and iOS apps from scratch. And these apps are actually the foundation of the apps that we now use today, that 8 years later, and it is what we are building off of in this day and age. A couple years later, so we have these native apps on iOS and Android, but a couple years later, starting from around 2013 to 2015, Facebook tries their hand at cross-platform yet again, this time with in-house built solutions with React and React Native. To provide some initial context, React is a JavaScript library that you can use to build interactive UI. It is commonly used to help build web interfaces. And then React Native is a framework that builds on top of that allows you to take the logic that you've built out for web and use that to actually render it in a native context. There is a slight difference, though, when we think about cross-platform solutions and HTML5 versus React Native. HTML5 is a much more pure web approach in thinking about this, where it's a much more simple wrapper around what is effectively a mobile website, versus React Native and all of its sort of sister frameworks is much more closer to working with the actual native components themselves. Today, React Native is used across a number of different surfaces within the Facebook family of apps, most notably the Marketplace app within the major app that actually, by and large, mostly uses React Native. And so similarly, we see a similar benefit here around being able to leverage code that you're writing with one platform and being able to use it in other places and reuse languages that are more familiar to web developers. And so after that, we have the next sort of iteration. So we're now at the point where we're 8 years into the life cycle of these apps. These apps have gone to the point where they're among the largest apps in the world, both in terms of the size of the code bases themselves, and then also as far as the number of people that are working on these apps at the same time. And so we're at the point now where Facebook these days invests a lot of time and energy and resources into building out a lot of both product and developer-facing infra in order to, one, improve the actual product experience of using these apps, but also at the same time to help enhance the developer productivity such that when you're working with an app of this size, of this scale, developers can still be productive, even despite how large it is. And so notable examples here include, on one hand, Hermes, which is a custom JavaScript engine that has been built to help improve the performance of React Native apps on Android and help to actually counter-effect some of the performance potential pitfalls of using a cross-platform framework. And then on the other hand, we also have tools like Buck, which is an in-house build system that was created initially for Android and has now later been ported over to iOS as well. And so we're now at the point in this day and age with Facebook where they're dealing with this massive amount of scale and have started to devise these solutions to help work around that type of scale. So next, we move from the sort of technical architecture and the different decisions that have been made there on that side and pivot a little bit more to talk about the monetization and business questions that Facebook ultimately had to answer when they made the shift over to mobile. So initially, when this was all happening 8 years ago in 2012, there were a lot of open questions as far as how Facebook was going to manage the shift over to mobile and how that was going to potentially impact the way that they made money. Facebook at the time had a really healthy degree of ad revenue coming in from web, and there are many open questions as far as how this was going to translate over to mobile. As you can see, when you're working with a web interface, there's much more screen real estate you can work with, right? There's the feed, there's the right-hand column ads. There's a lot more places where you can put ad inventory and a lot more opportunities to show ads. This, when you compare it to the mobile world, offers some interesting questions because you have much less space that you need to work with. And so there are these very big questions as far as how Facebook was going to figure out how to make this jump without letting their advertising revenue tank. The uncertainty was so big to the point where 6 months after Facebook had IPO'd as a company, its stock had actually dropped 50% because people were not quite sure how they were going to manage this transition. Fast forward a couple years later, the company continues to introduce things like feed ads. It starts to explore different new formats of ads that can go within this vehicle. One really interesting notable example here is that they came up with was this notion of app install ads. These days when we see them, it feels, it's something that we're somewhat familiar with, but this actually ended up being a very novel breakthrough way as far as an ad format, because this allowed app developers essentially to be able to market and promote their apps and find new users, which actually ended up being a really great fit for the mobile gaming industry, actually. So a little bit of an aside, but when you think about the way the mobile gaming industry makes money, oftentimes there's a very big head factor where there are a very small number of digital whales, as it were, that essentially are people that are, it's a very small set of users that are highly engaged with the app. They spend a lot of money on the particular apps. They're extremely active. And when you think about how much money these gaming companies get, a very large percent of it is driven by a very small number of people. And so these app install ads work really well for the gaming industry in the sense that it allows them to target, identify, and find people who are likely going to fall in that bucket and find them as users so that they can get them onto their particular games. And so when we think about mobile, Facebook and mobile and how it was able to manage these challenges today, we see that the script has actually almost completely flipped, where way back when, 8 years ago, Facebook had effectively all of its revenue on web and nothing on mobile, to the point now where, as of late last year, Facebook has actually booked 94% of its advertising revenue through mobile channels. And so next, I wanted to do a really quick note around culture and how the nature of which Facebook actually develops some of its products. So when we think about all these different previous phases of evolution, right, from a technical angle, from a strategic angle, from a sort of business angle, we can see a lot of Facebook's culture at play here around the way in which they, really prioritize constant experimentation, lots of innovation, lots of risk-taking, lots of trying out of new ideas. And so when we think about Facebook today, oftentimes we see it as this very large behemoth, right? It's this massive success with all these major apps that serve billions of users a day. But as far as we've seen, right, in the conversation that we've just had, Facebook the path to get to that particular point has not necessarily been very linear. Facebook has had its fair share of epic failures, of bad decisions, of mistakes that it's made along the way. But ultimately, at the end of the day, they were able to get to the point that they're at today. This is actually one interesting lesson that we can all sort of take personally for ourselves around, in this day and age when we live, more public lives than ever, when it feels like the stakes for failure are higher than ever because, it's much more obvious when we do fail. It can be very tempting for us sometimes to go with the safe option, to go with the safe path that no one would ever fault us for. But the examples that Facebook has sort of, shown us here are that there can be a lot of value in taking that risk, in taking that leap of faith, because there can be potentially a lot of value in, seeing where you end up after that, because it could end up in a much better place than where you started. And so where does that leave Facebook today, right? Facebook is, of course, no longer just an upstart in the mobile space. It's no longer just a sort of fledgling player, but instead is operating one of the largest apps, one of the largest services in the world. And so there are a couple of key areas that Facebook continues to struggle with even to this day. Of course, I mentioned a bunch around the technical scale challenges that we're running into. In my particular space, in developer tooling, this ultimately means building out a lot of in-house solutions and products and services around things like source control, around continuous integration, around the way we do testing, around the way we edit code, because we're at the point now where off-the-shelf components, off-the-shelf solutions from outside vendors no longer work for a company at the scale that we're working at. And then next, with Facebook becoming even more of a central part of our society, there's been much more scrutiny over time around the way in which Facebook creates and moderates policy around things like hate speech, censorship, misinformation, and all kinds of different levels of unsavory speech. The challenging here is that with these particular types of questions, with these particular types of topics, there are oftentimes no very clear right answers. There's just many different layers of gray. And the Facebook model of being very iterative, of figuring it out as you go, that model doesn't really translate very well when you're operating at this scale now, when you're governing basically a platform that's used globally, and where the stakes of failure are much higher and much more visible. And so that's one thing that they are continuing to wrestle with today, and there are very many open questions as far as how they will address that. Outside of that, there are also really interesting questions around quality and testing, because Facebook culture it would be surprising, but for a very large company, it actually does not have a lot of process. It actually does not have any very formal QA processes. And instead, right now, they rely a lot off of user testing, off of dog fooding, off of getting feedback from users. And so as Facebook continues to become a more integral service in people's lives, there's this interesting challenge they've had to do, culturally speaking, to figure out how to instill quality into the mobile development workflow and to really install much more robust testing practices in general. And so with that said, that is a little bit about Facebook, and then now we'll sort of pivot and talk a little bit more about Airbnb, which is a company that I've gotten to know a little bit better over the last couple of months, that also provides some interesting contrast relative to Facebook. And so with Airbnb was also a web-only property. It also jumped onto the mobile bandwagon pretty early on in 2012. And at the time, they were I actually hear from some of my colleagues that some of the first apps were actually very much so built by interns, and some of the foundations of which built by those interns are still in place today. Secondly, also, as Swift and Kotlin were introduced and became a lot more mainstream in the last couple of years, Airbnb jumped over to starting to use these technologies for iOS and Android pretty early on. Of course, this transition is a lot easier to make, though, when your organization is a lot smaller. Airbnb operates on the order of, I think it has less than 200 mobile developers. This is in stark contrast to Facebook, which is still, for the most part, very much so an Objective-C and a Java house, and where they're operating at the scale instead of thousands of developers, where it's much harder to move people over. So Airbnb has these native iOS and Android apps. They also, too, a couple years ago, they also try their hand at cross-platform in the form of React Native as well. The thinking was here that Airbnb at the time, they had far more mobile work to do than they had mobile developers to do it. And on top of that, their web stack was also already using React. And so it was a natural no-brainer for them to go down the React Native path and actually start to figure out how they could use more of the web talent that they had and parlay that over to building out more functionality on native. And so they started doing that for a couple years, but then as of actually 2 years ago in 2018, Airbnb ultimately decided to pull the plug on React Native. They actually wrote a couple of interesting blog posts sort of detailing their decision, but the long and short of it was what they ended up finding was that instead of the promise of having one stack to really worry about with JavaScript and React, instead they found that they were managing not just one and not just two stacks, but actually 3 stacks, where they had to think about their React and React Native portion of their code in addition to the actual remaining iOS and Android native code that they still had to manage. And so one interesting general note about cross-platform, after having seen all these different companies try these different variations of cross-platform, is that React Native and its sister frameworks with Flutter from Google and Xamarin from Microsoft, they all have their sort of place, and it seems like the sort of sweet spot for these types of frameworks is when you have a much smaller app, a much smaller, simpler app, and a much smaller development team to work with. I think it feels like any time you start getting more complex than that in the functionality that you need to have in your app, and the larger of a development team that you have, oftentimes it ends up potentially being more work and more complexity than it's worth to manage this interim layer versus just going full native instead. And so lastly, that brings us to the modern day, where Airbnb has now gone to the point where they've pulled out all of their React Native code in the code base, and they're instead investing a lot more and doubling down a lot more into this idea of server-side rendering, which allows you to get some of those cross-platform benefits without necessarily needing to use a cross-platform framework. The idea here with server-side rendering is that you are still able to leverage the web and the backend for a lot more of that logic and rely less on the client. And you're also able to, once again, decouple yourself from that mobile release cycle. And the way that it works in a nutshell is that you have your backend, which sends the client data in the form of components to render, the configuration of the screen, some different actions that can occur from that. And from there, the client then takes that data and then renders it on the screen. At Airbnb, the way that they do server-side rendering is through the system called the DLS, which stands for the Design Language System, that is used across both web and web, or it's used across both mobile and for web in actually rendering all of its different visual surfaces. And so as far as the current challenges that Airbnb is currently running into, one thing, it's sort of similar to Facebook in the sense that, these apps are now 8 years into its life cycle. These apps have started to get larger and larger to the point where a lot of this functionality is starting to get very intertwined and very messy and not very well encapsulated. From a user perspective, it's not quite so obvious, but from a developer productivity angle, this has pretty severe impacts in the sense that developers now have to work on the order of the entire app as opposed to just being able to work on the features that they want to work on. And so this results in really very annoying issues around editing, where oftentimes Xcode and IntelliJ can be really slow, or where features don't really work very well, and also in the form of build times, where you now have to build the entire app as you're iterating on a feature, instead of just being able to build your specific feature itself. And so one major initiative we're driving right now to try and fix and solve this is this effort around modularization, around platformization, so that we can better encapsulate these different features, better encapsulate logic so that it is well encapsulated in modules that developers can then use and work off of. This is likely not going to be something that will have a very obvious user impact and effect, but this really will set the foundation for enhanced mobile developer productivity down the road and really set the foundation for that. And so lastly, this brings us to a couple final notes around culture and how Airbnb thinks about and gets work done, and how it thinks about product development. And so Airbnb is very famously very design-driven. It places a very strong emphasis on aesthetics, on design, on the user experience, both in terms of its online surfaces and what those look like in its web product and its its mobile product, but also in its offline experiences and what that experience feels like when you're in a home, when you're on an experience. And the thinking behind this is that Airbnb obviously competes in an extremely competitive travel industry, right? They're competing against all sorts of different competitors, like hotels, like Expedia, like also tour guide operators that are offering experiences. And the thinking is that this attention to detail is ultimately what will help differentiate Airbnb and its offering relative to the other offerings out there on the market. And another axis for comparison across Airbnb versus Facebook is also on the way both companies think about their product development philosophy. Facebook is very famously all about scale, right? When you think about designing a new feature, when you think about launching something new, you're very much so pushed and encouraged to think about building for scale on day one. So for example, when they launched the Friends video feature, they had to work a lot with infrastructure to make sure that we had a scalable way to make sure we had enough capacity to create the videos in the first place, and then also to serve them to all the users that would see them. And so this is in stark contrast, right, to many other services and companies that you oftentimes see, struggling to keep up with load and capacity on the first day of launch. One, I think, more recent example of this is the Disney Plus launch, when they launched the new Disney streaming service that I heard ended up going down in its first couple days because there's just so much demand and so much load that they weren't able to deal with it. And so that is Facebook in a nutshell. They care a lot about scale and making sure that things will work at a very large basis. And this is in stark contrast to the way Airbnb thinks about product development, which in fact is almost the complete opposite. Instead, they think a lot more about trying to ideate and brainstorm and think about the ideal perfect experience for a user, even if it will not scale at all, right? Even if it's something that you cannot do on the scale of millions or even thousands of users. With the idea that you craft the ideal situation and experience first, and you figure out how you can work backwards and actually work in some of that magic into the product itself. This ultimately, I think, results in, it sort of shows the difference in perspective for both companies. Airbnb is very much so about making sure that they've sanded down all those rough edges, making sure that the experience feels as polished as it needs to be, which makes sense, right, when you are dealing with lots of money at stake and a travel experience that is not going to come around very often. And this is in comparison to Facebook, where they're much more okay with some rough edges in the experience. They're a little bit more okay if the app crashes a little bit more because it's a much more high-frequency product that people keep using. And so with that, I think one thing that I've learned and one thing that's been very educational for me, having worked at both these companies and experienced both of these different cultures, is that there is no clear universal right answer, right, to any of these problems, to any of the strategic problems, to any of the culture problems and questions, and to any of the technical questions as well. It all ultimately comes down to the situation that you're in, the context in which you're operating, and the approach that will work best for that particular scenario. So in the Facebook model, this probably means moving really fast, experimenting a lot, and really designing for scale because this is the nature of the product that exists. Versus on the Airbnb side, really putting the 80-20 rule aside and really caring about all the different aspects of a particular experience and making sure that experience is as ideal and as perfect as possible. And so with that actually concludes the end of my talk. I hope you got some interesting nuggets in there about whether it's the evolution of mobile or some interesting tidbits from the evolution of Facebook or Airbnb. Thank you so much for your time. And yeah, I'm open for questions if there are any. Thank you.
Does anyone have any questions for Stephanie? Oh, okay.
Hi, Stephanie.
Hello.
Hang on a second. Okay, so with the increase of folding phones in the market, how do we approach our existing technology to adapt to this new one?
When we think about all these different, are you saying as far as within these apps, how we think about taking advantage of these different capabilities?
Exactly.
That's an interesting one. I think I think we see, so it really depends obviously on the company, right, and the specific area that they're in, what they're ultimately trying to do. We do see a lot of companies really trying to take advantage of new tech, right? So one key example that I can think of off the top of my head is with Facebook and the emergence of AR, VR as a technology. One thing that I've seen was there's been some really interesting use cases that I've seen emerge. Obviously, there are the very obvious examples around all the different lenses and filters you now see on not only products like Snapchat, but also Messenger and all the other Facebook products. But I think some interesting opportunities that I also see are, being able to leverage that in other sorts of applications that are maybe a little bit more practical than just communication and entertainment. One related example to that I can, for whatever reason, think off the top of my head is, for example, trying on lipstick, right, and being able to experience, the art, the practice of being able to, try out a new product and see what that might look like on yourself without needing to go to a store. That is something you can now do with AR. That is now possible in a number of different apps. And so I think that it really depends on obviously the different areas that your company and your product is operating in and what that ultimately means. But yeah, that is one particular area. Another thing that we also see is around ML, right, and AI, and being able to do more of that on the devices themselves. Obviously, that is going to require still a lot of innovation as far as being able to do a lot more inference in actually edge devices and things like that. But I think there is a lot of promise there, and I'm very curious to see where that goes in the future.
Okay, thank you. Does anyone has questions? No?
Okay, then a big round of applause for Stephanie.
Thank you.
Don't leave the auditorium just yet. We're going to give away the prize associated with this keynote. So if we read your QR code, don't leave the auditorium just yet. Give us 1 minute and a half. Okay, so we're going to give away the prize now associated with Stephanie's keynote. So let's see who's going to win. Drum roll, even there's none, of course. So let's see. I'm going to pick a winner right now. I think this person is not here anymore since I saw her leave. So we're going to re-roll. Okay, try two. Francisco Matos. Please, to receive your award, go talk to the people up there who have the SINFO badge. Please. There's also, if you want to ask Stephanie questions, you can also go to the Torch Showcase area. Sorry, I forgot. Torch Showcase area to meet her. Thank you so much for coming to the first day of SINFO. Tomorrow there's more keynotes, there's more presentations, more workshops, more prizes to be won. So we hope to see you tomorrow. So yeah, thank you so much for coming.
O nosso maior ativo são as pessoas. A atitude marca a diferença. O teu ritmo, a nossa harmonia. O teu talento, a nossa paixão. O teu crescimento, a nossa partilha. O teu futuro, a nossa visão. Qual é a tua atitude? Na Everis, o futuro é teu. Traz a tua atitude.